finally got the RTC to work. Hello, and in this video I will be covering how to set up the I2C bus. First, let's go over the hardware connections. I have an FTDI connected to RC6 and RC7, and then a real-time clock connected to RC3 and RC4, which are the clock and the data lines for the I2C bus. Now the RTC is a standard DS1307 with two pull-up resistors connected to the SDA and SCL lines and the crystal connected as well. Now let's have a look at the data sheet. Now the I2C bus is controlled by 6 registers, which is MSSP control register 1 and 2, and then MSSP status register, and then the serial transmit receive buffer, SSP buff. Then we have our shift register, which we can't directly access, and then the address register for the I2C bus. The address register is used also for generating the clock in master mode. The first register we're going to have a look at is MSSP status register, and we are going to disable this because we are going to use a 100 kHz frequency. It's only used when we're using a 300 kHz frequency. This just basically controls the angle of the rising of the clock. And then we have the SM bus select bit, which we are going to disable, since this is a different type of protocol than your standard I2C protocol. Then we have bit 5, 4, and 3, which are relevant for master mode. Then in bit 2, the read-write information bit is going to tell us if we have a transmit in progress or if no transmit is in progress. Bit 1 is also irrelevant in master mode. And then in bit 0, the buffer full status bit gives us an indication if the data in SSP buff has been shifted out or if data has been shifted in to the buffer for transmit and receive. So it will be an inverse check. So if we are transmitting, we're waiting for the buffer to be empty. And if we are receiving, we're waiting for the buffer to become full. Now in the control register 1, I'm not going to do error handling, so I'm going to class bit 7 as irrelevant. Bit 6 also irrelevant. Bit 5 master synchronous serial port enable is then able to turn RC4 and RC3 into the SDA and SCL pins. Otherwise they're configured as normal GPIO. But then we have bit 3 to 0, which is our mode select, and we're going to select master mode, and they also give the formula to calculate the clock frequency of SCL. And then in control register 2, we have a bunch of status bits. Okay, bit 7 we're not going to use. Bit 6 is the acknowledge status bit. This checks if we have received an acknowledge from the RTC or any other I2C device on the line. Then we have the ACDT, which is acknowledge data bit. This just checks if the master has acknowledged. Then bit 4 is the acknowledge enable. This starts an acknowledge sequence from master to slave. And then bit 3 is the receive enable bit, which puts the master into receive mode to get data from the I2C slave. And then we have bit 2, and this initiates a stop condition on the I2C line. And we have the RS send bit, which is a repeated start condition enable, which starts a repeated start on the I2C line. And then we have bit 0, which is the send bit, which enables a start condition on the line. Then we go down for the specifics. And then the specifics for master mode is that the module, when it's configured, it does not allow for event queuing. So you can't like send a start stop condition or a write condition in sequence. You need to check if the I2C line is in an idle state, which is done via control register 2, and if no transmit is in progress. Otherwise you're going to hang your I2C line. And then we have the baud rate. When a write occurs to the SSP buff, the baud rate generator will automatically begin. So we just need to put data in the SSP buff and then a transmit will start unless we are in receive mode. And here they just state if we try to put the device in receive mode while the bus line is not in an idle state, it will not take effect and one of the error flags will go high. Here they specifically state that when you want to go into receive mode, that you need to have the bus in an idle state. As they say, Must be in idle state before blah blah blah. Otherwise, anything on RSEN will be disregarded. Now, after data has been clocked in from a safe device, the contents of the shift register is loaded into the SSP buff and the BF flag bit is set. The data you want will be located in the SSP buff and the BF flag will indicate to you when you can read from the buffer. Now let's quickly go over the real-time clock. This real-time clock is the common DS1307. Now what I'm interested in only is the I2C protocol on it. Okay, here's a table of the registers and what is contained in the 8-bit values of the registers. If we just go a bit up, we are going to want to set bit 7 of register 0 to 0, because when it is 1, there is no counting on the clock, which is effectively a dead IC. And then the date format, if you directly read it, is in this format. I'm going to change the date to something I can read, because that's just confusing. And then bit 6 is the hour register, which is either in 12 or 24 hour mode, and I'm going to set it to 24 hour mode by clearing bit 6. Then we look at the data write. We have our write address here, and then the sequence to write to the device, and then a sequence to above it to receive data from the device. Then we have the protocol to set where to start reading on the device. So typically you will say start reading from address 0 to, and then it auto increments the address as you read from it after every acknowledge. So say we have an address of 0 here, then this first section will be address 0, and then the second will address 1, address 2, and then so on until you send a not acknowledge and a stop condition. This not acknowledge at the end just hangs the bus and just stops the RTC from transmitting data over the line. Now let's get to coding. Now a quick overview of what's going on in the code. I have my UART data variable set here. The high and low priority interrupts function definitions. The clock set to 8 MHz, and then just the startup delay so I don't have random printouts on PuTTY. And then TRISB set as outputs and TRISB set to low. This is just because I have the LEDs connected and they are irrelevant for this tutorial. Then we initialize the UART at the board of 96. Just a printout to indicate my program has started. The interrupt enables. And then a detection if UART data has been received, which I'm not going to use. And then in a high priority interrupt, we pull the data from the UART. So first we're going to start with the I2C initialization. So we start with void I2C init. And we're passing it no parameters, so void. Now the first thing we want to set is our pins as input. So we start with tris cbits dot rc3 is equals to 1. Copy the line, paste it, change the member to rc4. Now the first thing we want to set is the slew rate control bit, which is located in SSP stat bits. Member SMP equals 1 to disable it. Change that to capital letters. Copy the line. And we disable the SM bus protocol with CKE equals 0. Then we go over to control register 1. We say SSP con 1 bits member SSPM. For the mode select, we say that's equals to 0x08. Then we set the SSPADD equal to 19, which is the clock frequency. I will show how that's calculated in a moment. And the last one is SSP con 1 bits member SSPen equals to 1 to enable the I2C bus. Now let me show you how this is calculated. Now to calculate the frequency of the SCL line, we use this formula. Then we have the manipulated over here to get the value of SSP add. We have 8 MHz divided by 4 times 1 kHz minus 1 equals to SSP add, which is 19, which will give us a clock frequency of 100 kHz. Now back to the code. Next we add in an idle check for the I2C bus, which is void I2C is idle. Now in this function we add while SSP con 2 and 0x1f, or SSP stat and 0x04. Now what this idle function does is it checks, is the start condition idle? Is the repeated start condition idle? Is the stop condition idle? Is the receive enable idle? Is the acknowledge enable idle? And is the acknowledge bit 0? Hence the 1f. And then the SSP stat checks if there is a transmit in progress. So it checks if all these conditions are 0, then we can proceed with doing the next instruction to the I2C bus. Now the next function we're going to do is enabling the start condition by adding void I2C underscore start, whilst at no parameters. Then we start by adding the I2C idle function, and then we initiate the start sequence with SSP con2 bits member sen equals to 1. And we add the next function for the repeated start condition. We call it void I2C rep start. The parameters, we again add a check if the I2C bus is idle. We copy the SSP2 con bits and we call it rsn equals 1. Now for the stop condition, we add void I2C stop void. Again, check if the bus is idle. Copy the SSP2 con bits, change it to member pen equals 1. Then we do a function for the I2C write, which is void I2C write. We pass it to uint 8 I2C data, and we start again. Bus is idle. Then we say SSP buff is equals to I2C data. Then we have our checks, which is while SSP stat but member bf is not equals 0. And we have our secondary check, which is SSP2 con bits member act stat is not equals 0. What the write does is check if idle, load data into the buffer that's going to be clocked out to the slave device. Check when the buffer is empty and check if the device has acknowledged the data. It is possible to hang the bus with this if you write incorrect data, so power on reset will be your best bet to get it working again. Then we have our next function, which is the I2C read, which will be uint 8 I2C read. And we pass it also uint 8 which is acknowledge. Then we declare a variable of uint 8 receive equals 0. And again we check if the I2C bus is idle. Then we use SSP2 con bits member rc sen equals to 1. And we add a check for our buffer until it is full with the bf bit. And we say receive is equals to SSP buff, which will now be holding our data. And we say SSP2 con bits ack enable is equals to acknowledge, well, ACK. And then we return receive. Just a quick recap of this function. We wait until the I2C is in idle state. We enable the receive. We wait for the buffer to fill up. Then we read out the buffer. And then we send and acknowledge to the slave device by setting ACK to either 1 to enable and acknowledge and 0 to disable and acknowledge. And then we just return our value. Then we go to the top and we add to defines RTC write ADDR and RTC read ADDR. Now the read and write are these two values indicated in the datasheet, 0xD0 and for a read 0xD1. Now we go to our main loop. Now the first thing we want to do in our main loop is add our I2C net function, and then after that we want to check if we can read from the I2C device. This is done by using I2C start and then I2C write. Copy the address above and then followed by another I2C write to address 00, which would be the seconds register, followed by an I2C repeated start, followed by another I2C write. We change the address to read address, and we say uint 8 seconds equals to I2C, let's go read, and then 0 for acknowledge, because this is the only byte we are reading, and then we send finally an I2C stop. And we quickly add a printout. Now we program the pick, and as you can see from above, we have our printout sec and 35, which tells us we have successfully read from the second register. Now the next thing I'm going to do is set the time and continuously read from it. Now we go up top. Now I'm going to copy paste the structure that I previously wrote. I'm copy pasting just for the sake of time, otherwise we're going to set till the cows come home. Paste in the structure. Now what this structure does is contains the data that we want to write to the RTC. So the high value for the years, the low value for the year, reserved bits that we can't use, the high value for month, the low value for month, again reserved bits we cannot use, the high value for date, low value for date, reserved bits we cannot use, the 3 bits for date, the single bit we can't use, the hour mode bit, and then the high value for hours, low value for hours, RFU single bit, again we can't use, the high value for minutes, the low value for minutes, the clock halt bit, and then the high second and low second. And then we declare a variable of our structure type, and we call it RTC data. Then we go down, then we add an array of uint 8, call it RTC buff. We make it an array of 7 bytes, and we set it all to 0. Then we add in memset reference RTC data, clear the entire structure, and we say size of RTC data, and I'm going to copy paste all the data that has been set up. Okay, now the data has been set up so that we start at second 00 at 15 minutes of the 23rd hour of the 7th day, this date of the 17th, the 11th month, and the 18th year. Then we add in a memory copy of RTC buff, and we copy RTC data into it, and size of RTC data, and we reference RTC data. Now we're going to write the data to the RTC setup. We are going to keep this piece of code for later. We keep this as is. We start at address 0, and we're going to write from RTC buff 0, and we repeat this line for 7 writes. We just change the array member. Then we just change the array member to send the data through, and then we add a stop. Now I'm just going to add a printout over here, which is just a new line print. And then in our infinite loop, we copy the start sequence. Then we move our code that we previously used to read the RTC. Then we copy our RTC buff. We replace the sec variable with RTC buff 0. We change acknowledge to 1. And we copy paste the reads again until we have 7. We have our stop condition at the end. And then we go back to our memory copy it, we paste it, and then we just swap the 2 variables around. Then I'm going to copy a printout from pre-written code. Okay, now this just prints out the date and time according to what's in the structure. And right under that we add a delay of 500 milliseconds. Now we program the pick, found a mistake. The last read should be 0, so we don't acknowledge on the last read. And as you can see from the PuTTY terminal, our date is set up, we are counting, and eventually it will roll over to 16 minutes and blah blah blah. And that's a basic introduction to using the I2C bus on a pick and using a DS1307 RTC. Any parts that I've used will be linked down in the description. Any code that I've written will be shared on my Git. A like, share, comment and subscription would be greatly appreciated. Thank you. Have a nice day.